Hello, everyone, and welcome back. In this lecture today, we are going to talk about one of my all-time favorite topics in all of mathematics, and that is the different sizes of infinity. And in particular, we're going to focus on what are called countable sets. Now, countable sets are the smallest size of infinity, and you can probably guess by the name countable, it means that we can sort of count the elements. And mathematically, what this means is that we can put the countable numbers, so that is the natural numbers, the counting numbers, in one-to-one correspondence with elements of another set which turn out to be countable. Now, we'll put all of these definitions together and we'll do a ton of examples in this lecture. But I just want to point out that this study of different sizes of infinity, and in particular countable sets versus what are called uncountable sets that can't be counted, has a long and rich history in mathematics that I highly recommend spending some time looking into. In fact, this was first introduced by Georg Cantor in the 1800s, who is potentially one of my favorite mathematicians, a very, very interesting and prolific figure in mathematics. But at the time, his genius was not necessarily recognized by the wider mathematical community. In fact, many people dismissed his work on these different sizes of infinity, and it wasn't until long after his death that this became commonly accepted and is now taught in, say, introductory real analysis classes like this one. So this is a very, very fascinating, and at one time it was a controversial topic. But now these are sort of widely held axioms of mathematics and ways of understanding the sizes of infinite sets. So let's go ahead, let's jump in, and let me at least first give you the definition of what it is that we're going to be talking about. So the definition for today is going to be that a set S, so S just stands for set, this thing is called countable if it is an infinite set. So of course, we're only going to talk about infinite sets today. If something is finite, it's not very interesting, right? I can just assign the numbers, say 1 to n for it, for which it is possible to arrange all the elements of S into a sequence. So we're back with sequences, right? Back where we started at the beginning of this class. So that is, S is countable if I can write S as just a sequence of elements, S1, S2, S3, and so on and so forth, all the way to infinity, with each element of S listed exactly once in the sequence. So listed exactly once in the sequence. Okay, so the way that you should think about this, again, is being able to count the elements of S. And we think about, sort of abstractly thinking about what counting does, is it assigns a natural number to an element of the set, right? So I say, I am the first person in the room, you are the second person in the room, so-and-so over there is the third person in the room. What we're doing is assigning each of us a number. It could be arbitrary, right? I started with myself, but I could have started with you as well. But the point is, I've assigned everybody a number. Well, that's the same thing that's happening with countability of sets. So you say, let n be a natural number. Then you are taking n and assigning an element in the set at S sub n to be the nth element of that set. So that means that you can count, you can use the counting numbers to assign the elements in your set. Okay, so of course, the first example, this is truly kind of silly almost, but n is countable. Well, of course, n is countable because n is just equal to 1, 2, 3, 4, right? So it is the counting numbers, right? It's kind of a silly, trivial thing to say, but it's important to note, right? And this is what we call the smallest infinite set, at least if we don't assume the axiom of choice and we sort of stay away from really sort of complicated mathematics. So at least for us, this is going to be the smallest infinite set. Okay, then let me give you another example. How about let's let E denote the set of all even natural numbers. So thus, I want you to first note that E is entirely contained in the natural numbers, right? 3 is not in there. So it is a proper subset, right? It doesn't include certain natural numbers, but it's still an infinite set. Now, if you think about what I just said, the natural numbers are sort of the smallest infinite set, but E is sort of smaller in some sense, right? There's this puzzling issue here. Well, I'm going to claim that E is countable. So in fact, so that means that I have to be able to sort of count the elements of E. I have to be able to list them in terms of natural numbers. I need to assign, this is the first even number, this is the second even number, the third even number, and so on and so forth. Well, in fact, the elements of E can be arranged in a sequence by means of a function. Remember, sequences can always just be thought of as functions from the natural numbers into, say, the set of real numbers. And this function is going to be S, which takes n, a natural number, and gives it 2n. And this thing gives you every single even number, right? So you say, put 1 into this function, it gives you 2. Put 2 into this function, it gives you 4. Put 3 into this function, it gives you 6. But that means that I have every single even number represented in here, right? 100, well, that means that I had to put 50 into this function, right? 200, well, I had to put 100 into the function. Everything is accounted for here. So thus, every element, every element of E is in the range of S. Therefore, E is countable. So what we've said is that, say, by our construction here, 2 is the first even number, 4 is the second even number, 6 is the third even number, right? So what we've done is we've taken the elements of E and we have assigned a natural number to them, and therefore we have been able to count them. Now, think about how crazy this is, right? This is a proper subset of the natural numbers, and yet it lies in one-to-one correspondence with the actual natural numbers. And this comes from the fact, again, that the natural numbers are the smallest infinity. So even if you have an infinite set that looks like it's smaller than your natural numbers, it is in fact still going to be countable. You can do the same thing with the odd numbers, right? Your function would just be 2n plus 1 or 2n minus 1, depending on how you want to arrange your starting value. But in that case, again, the odd numbers are themselves a countable set. And this is the weird thing, right? Because the even numbers are countable, the odd numbers are countable. When I put those two things together, I get a bigger infinite set, but it's still countable. that is very, very interesting, right? I want you to sort of wrap your head around this. This is the mind-blowing nature of what Cantor was getting into in the 1800s. And just think about how insane this probably was and how revolutionary this was to mathematics at the time. Okay, let me give you another example, right? So I'm going to skip over the integers. I want you to try and show that the integers themselves are countable. And let's skip into, I'm going to start with the positive rational numbers. So let's say let Q plus be the strictly positive rational numbers. I'll get to the full rational numbers after this, but I want to say that if Q plus is the positive rational numbers, I claim, or we claim, Q plus is countable. So this is pretty crazy, right? This is every possible positive fraction. 1/8, 277 over 1,630,523. You know, these are all elements here. This is a huge, 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 huge set, but it's still countable. That is the craziest thing about all this. Okay, so first note that Q plus, this is equal to the set of n over m, which is for which n and m are both natural numbers. Okay, so in some sense, you can think of this is the sort of natural numbers times or crossed with the natural numbers, right? You take one natural number n, you take another natural number m, you divide them, and you get a positive rational number. This is an enormous set. Okay. Now I need a fresh new page to do this. Let me show you how you're going to do this. And it's done sort of pictorially, which kind of makes it a little bit more fun. So let us arrange the elements. Oh, sorry, the elements of Q plus as follows. Okay, so I'm going to arrange everything in a huge, huge, huge matrix. Okay, so the first thing that I will do is I will say in the rows here, that is the value of m. So I'm going to say m equal to 1 in the first row. And in the columns, this is the values of n. So this is n is equal to 1. Maybe I won't put the colon here. N is equal to 2. N is equal to 3. N is equal to 4, and I'll just do that for now. And I'll say m is equal to 2 here, m is equal to 3 here, m is equal to 4 here, and so on and so forth. Now I get to pick every possible natural number. So these things, this is an infinite matrix, if you want to think of it that way. Well, this becomes 1/1, which is just 1. I'm not going to write it as 1/1. This becomes, do we put n or m on the top? Yeah, n is on the top, so this becomes 2. This becomes 3, 4. So in the first row, I've listed every single natural number. Then in the second row, I have every natural number divided by 2. Now I'm going to write this as 2/2. So this is just 1, but I'll write it that way just so you can see how I'm arranging this. 3/2, 4/2. Again, that's just a half, but I'm not going to reduce any fractions for now. And here I'm taking every natural number and dividing it by 3. So I get 3/3, 4/3, and so on and so forth. And here again, I've got 2/4. So I'm not reducing any fractions. I'm just keeping everything as is. And you can see every rational number, every positive rational number is in there, right? So if I have n divided by m, that is in the nth column and the mth row. So it's there, right? 100 over 101, for example. 100th column, go down to the 101st row. It's in there. Every single rational number is in there. Now, of course, there's repeats in here as well, right? And that is that's fine. So if we look back at the definition, it says everything is listed exactly once. Well, here's what we're going to do. I'm going to make a sequence out of everything that's in this matrix. And then you can just move to a subsequence by pruning out the elements that are repeated, right? So you can see 1 is represented across all of the diagonal here. So that means that you can just prune out the 1, you move to a subsequence. So the idea here is we're sort of over counting everything. But again, we've seen that the natural numbers are the smallest set of infinity. So even if we move to a proper subset of what's represented here, it's still going to be countable. That's what we saw with the even and the odd numbers in the previous example as well. So if I can make everything listed in this matrix countable, then I can make the whole thing countable just by pruning out the duplicates. Okay, so the question is, how am I going to do this, right? Because if I just start counting across a row, well, I'm just going to be counting forever. And so that means I'll never get to the second row. Similarly, if I start counting down a column, I'll be counting forever and I'll never get to the second column. So you have to be very, very strategic about this. How are we going to set up a sequence so that we crawl over every single element and still make sure everything is accounted for here? Well, I'm going to start in the top right corner. And I'm going to set, maybe I'll keep it in green. So I'm going to set the first element of my sequence is equal to 1. Well, then the second element of my sequence, I'm going to move over to the right. I'm going to pick 2. Now you might be thinking, this is exactly what you told me not to do, Jason. You are going across the rows. But let me show you what I'll do next. I'm going to go down to 1/2. So S3 is equal to 1/2. Then what I'll do is I'll move down to 1/3. So S4 is equal to 1/3. Then I will move up to 2/2. So again, that's a duplicate. That's fine with me. Then I will move up to 3, which is 3/1. So this is S6, which is 3. I'll write it as 3/1 here because I want to show you where the pattern is. And then the next one, if you can maybe guess what's going to happen, I'm going to move over to 4. And this gives me, I'll again say 4/1 just so you can see the pattern. And here, then I go down the diagonal again. So I'm just going to write it out. And then I move down and then up. And I continue on this little path of sweeping over these diagonals. And what you can see from this process is I'm going to get everything in here. It's going to be hard to pinpoint where it is in the sequence, but if I just sort of repeat this process sort of inductively, then I'm going to crawl over the whole matrix, right? Because all I'm doing is zigzagging across these sort of backwards diagonals in the matrix. Now, what is it that I'm doing here? Well, let me put underneath, how do we know where things are in the sequence? 1/1, that is the same as you take n plus m, and this is equal to 2, right? So n is equal to 1, and m is equal to 1 in this case, because because we have 1/1 in the top corner. Then the next diagonal, the 2 and the 1/2, that's 2/1 and 1/2. Well, in this case, this is the n plus m is equal to 3 case. Then the next diagonal, so S4, S5, and S6, this is 1/3, 2/2, and 3/1. In this case, you have m plus m is equal to 4. And you're probably getting it now, right? Because the next case is n plus m is equal to 5. And so what we're doing is we are listing in this sequence all of the combinations of n and m that add up to each natural number. So we start at 2. We ask, what are all of the possibilities for n and m being natural numbers that add up to 2? There's only one. All right, list it, move on. So what you can see from this sequence is we actually didn't need the matrix. The matrix is a visual representation of what's happening here, but the real process is actually following this procedure of n plus m is equal to each natural number. And you step up that natural number and you list all of the choices for that natural number, and then you continue on. Now, what you can see is that for each natural number, so say k, there are k minus 1 that you're listing in here. Okay, so there's only one here, so only one. Here, there are two elements, or two choices of n and m. Here, there are three elements. And then here, there will be four elements. And so you have this sort of telescoping series, right? If I want to know all of the n plus m's that add up to 100, well, there's going to be 99 of them, right? You can sort of just cycle over the values of n and m. N is equal to 1, m is equal to 99, n is equal to 2, n is equal to, or sorry, m is equal to 98. But the point is, I did it, right? I made a sequence. I can't write it all down. I can't, if you give me, 101 over a billion and 63 or whatever that number is, I can't tell you exactly where it is. That's okay. We do this in math all the time, right? This is sort of an inductively defined thing. And so as long as I know where I was on the previous step, so n plus m equal to 100, then I can start listing n plus m equal to 101. And this tells you that the positive rational numbers are themselves countable. Well, then a direct corollary of this fact is that Q, the entire set of rational numbers, is also countable. Okay, so how do we prove this? Well, notice that Q is equal to Q plus, which I already showed was countable, plus Q minus, which is all the negative rational numbers, plus 0. All right, so I'm using set notation of unions here. And we can say that an element, say x, is in the negative rationals if and only if negative x belongs to the positive rationals. Of course, that makes sense, right? Minus 1/2, well, you make that a negative, you multiply that by minus 1, it becomes positive 1/2, and it was accounted for in the positive rationals. So also, Q plus is equal to, now we can list the elements. We just said that it's countable. So let's say this is Q1, Q2, Q3, Q4, and so on and so forth, since it is countable. Okay, so again, we're just sort of breaking Q up into its constituent components. And in the previous example, we just showed that Q plus is countable. So I can list the elements as a sequence, right? That's what this tells me. Well, then list the elements of Q as, okay, well, I'm going to do S1 is equal to 0. So I started with the 0 element. That's good. And then we'll say S2 is equal to Q1. And then S3 is equal to minus Q1. So I want you to notice this, maybe we'll put this in red underneath. This is in Q plus. This is in Q minus. And then the next one, you might be able to guess where this is going. S4 is equal to Q2. S5 is equal to it's equal to minus Q2. And so on and so forth. So what's the actual pattern here? So in general, S1 is equal to 0. S2n is equal to Q sub n, which belongs to Q plus, and S2n plus 1 is equal to minus Qn, which is in Q minus. Now, if you look at that sequence, this tells you that you can find every rational number in there. Because if it's a positive rational number, it's listed in the even terms. If it's a negative rational number, it's listed in the odd terms. And if it's 0, it's at the beginning of your sequence. So therefore, Q is countable because I'm able to list every element of the rational numbers here. And it just comes from the fact that I broke it up into the positive ones, the negative ones, and 0. And now I've got a way of identifying everything. And what I want you to try and do is maybe pause the video and use this same technique to show that the integers are countable using the fact that the natural numbers are countable. It should be a very, very similar process to what I just did here. Now, here's the thing. We're going to use this idea. Remember, the rational numbers are dense in the real numbers, right? That says that they can be used to approximate the real numbers. But also, this tells us that the rational numbers are small in some sense, right? This is a really, really strange thing. They're countable. They're a small set of infinity. Now, what we're going to do is we're going to use this fact to find something that is both open and dense in the real numbers, but yet it's going to be kind of small again, because it's going to be built from countable numbers. So we will describe a set O, so O, that is both open, so remember this from the previous lecture, and it's going to be dense in the real numbers, yet which is quite, now I'm going to sort of put this in quotation small, and you'll see why I say it's quite small here in a second. Okay, so what we would like to do is we would like to find something that is open, it's dense, but yet it doesn't have a whole lot of width to it. Okay, so what is it that I mean by width? Well, here, let me show you. Okay, so let's let epsilon be a small positive number. So you get to pick it. This is where the sort of smallness of this set is going to come into play. Okay, so I'm going to say consider the interval, or we'll call it a line segment in this case, just because we're thinking about length here. So the interval from 0 to epsilon, it's non-zero, it has length epsilon. So this is of length epsilon. Then we will construct a sequence. So I'm just going to try and explain to you what I mean by small here. We will construct a sequence of intervals AK, BK, each of length epsilon over 2K. So what this means, so that is the first interval, A1, B1, has length epsilon over 2. Right? The second interval, which is A2, B2, has length epsilon over 4, and so on. But what we know here is that when we take the union of all of these intervals, so the union of all of these intervals is open, because it's a union of open sets. Remember, we proved this in the previous lecture. And the length is, I'm going to put this in quotations, right? So if you line up all of these intervals end to end, the length is the sum of epsilon over 2 to the k, equal 1 to infinity. I'm going over all the natural numbers, which you might remember this from geometric series, but this is equal to epsilon, the same length as the small interval 0 to epsilon. So I can make an open set where all of these intervals are sort of half as small as the previous one, so that when you add all these things up tip to tail, they have a very, very tiny length, right? Their length is just the same as the line segment 0 to epsilon. So that, that little intro paragraph here, I just want you to understand, this is what I mean by a small set. And this can be as small as you want. Maybe I want to take epsilon equal to 0.1, but you want to take epsilon to be 10 to the minus 20. You want it to be so ridiculously small. Well, that's perfectly fine, right? Epsilon is a positive number, and that's going to work here. Okay, so how are we going to construct this? Well, so let's set, so since we proved that the rational numbers are countable, let's enumerate them. All right, we have a way of listing out all the elements. It doesn't matter how you list them. The fact is, it's countable. This is, so which can be arranged since Q is countable. Okay, let's define each of these intervals. So let A1, B1 be centered at S1. So S1 is the midpoint of this interval with width or with length epsilon over 2. And A2, B2 be centered at S2 with length epsilon over 4, and so on. I think you get the idea, right? The idea here is that those intervals that I talked about above that are going to have length epsilon over 2, epsilon over 4, epsilon over 8, et cetera, you pick each one of the rational numbers that you've enumerated as the center of each one. And then this tells us that from above, this union of all of these intervals is going to be small, right? It's going to have length epsilon. Now, the fact that this thing is dense just comes from the fact that the rational numbers are contained in this. So notice the rational numbers are contained in this union of all of these intervals. And since Q is dense in R, all right, I don't want to squeeze anything more in. I'm going to go to the next page here. We find that O equal to this union of all these open sets is also dense. Now, why is that the case? Well, if you can use elements of the rational numbers to approximate every single real number, then that means you can just extract sequences of rational numbers from the set O, because it contains all of the rationals, to approximate any real number. So again, because O contains the rational numbers, it itself is a dense set because it can approximate any rational, or sorry, any real number. But also, O is open. So this is open since each AK, BK is open, right? We proved this in the previous lecture. We said that any collection of open sets, if you take unions of open sets, you still get open sets. And so therefore we have constructed a open, dense, small set. And this small could be as small as you want, right? You get to pick epsilon. You can still always construct this set. Okay, so that was cute, right? It was kind of a cool little application of the things that we've seen so far. But what I want to point out is that, with the number systems we've seen so far, the natural numbers, even the odd numbers, the rational numbers, even I alluded to the integers here, they're all countable. So, you might be tempted to just think, well, maybe all infinity is countable, right? Maybe everything is just countable. Well, what I'm going to show you is that that is not true. So this is what's known as Cantor's theorem. And Cantor's theorem tells you that you can't count the real numbers. So the set R of real numbers is uncountable. That means you can't count it. So it is impossible to include all real numbers in a sequence. So you can't do it. You can't build a sequence that includes every single real number. Now, what we showed with the previous examples are that you can build a sequence of all rational numbers, right? I did it. I constructed it. I did it with a picture, and then I showed you what the process was. This is in this case, you can't do it for real numbers. The real numbers are bigger. They are what are called uncountable. Now, you can go really down the rabbit hole with this stuff, and you can find some really, really cool mathematical literature. We're not going to delve into this. We're just going to deal with the case of countable versus uncountable. But there are things called, there's something called a continuum hypothesis, which asks if there are infinite sets that have sizes between the countable natural numbers and the uncountable real numbers. And so things get very, very complicated, very, very fast. We're not going to delve into that. We're just going to deal with the countable versus uncountable case. Okay, so first of all, let's look at some issues that may arise. Okay, so we begin by noting, so I just want to point some little pieces out before we go down this, that the possibly endless decimal expansions, right? So real numbers, this includes things like pi that have infinite decimal expansions that don't repeat. There's no patterns, right? These are very, very complicated. Of real numbers are not unique. You may have seen this before, right? Because an infinite tail of nines, you'll see why this is important in a second, okay? So bear with me. So an infinite tail of nines can always be replaced by an expansion in an infinite tail of zeros. Now, you may have seen this. So for example, this is a very, very common one in mathematics. A lot of people have trouble with this one. But if you take 0.9999 all the way out, this is actually just equal to 1. So we're not going to get into the proof of that, but this is true, right? You might have to look this up on your own, but this is a very, very well-known thing. So this tells us that there are non-unique ways of representing real numbers, right? If I want to represent 3.14, I could do this as 3.13 with all nines repeated, or I could do 3.14000000, right? This is an issue. This becomes a little bit of an issue when we're going to talk about real numbers here. Now, moreover, every infinite decimal expansion. So wait, sorry, I should conclude that. So we will not include endless tails of 9. Okay, so I want to get this out right here. So you're not allowed to give me a number that ends in nines. I'm going to turn that into the one that ends in zeros. And this implies that decimal expansions of real numbers are unique, right? So if you are going to talk about the number 1, the only way to represent it is 1.00 with zeros all the way to infinity. I'm not allowing you to write it as 0.9 with nines repeated. Okay, that's the point here, right? I just want to get the ground rules down because you're going to see why this is important in a moment. Now, moreover, if you allow for this, every infinite decimal expansion represents or representation, decimal expansion corresponds to a real number. So you can do whatever you want, right? 1.235876217, whatever, right? All the way out, that is a real number. As long as it didn't end with all nines, you're good, right? That's a unique representation that gives us how to represent real numbers. Okay, so let's assume that Cantor's theorem is false. So now we suppose, so we have the ground rules down. We suppose Cantor's theorem is false. Okay, so that means that the real numbers, so suppose, therefore, that the real numbers, they can be placed into a sequence. Okay, so I said every real number can be written as an element of a sequence. So x1 is a real number, x2 is a real number, x3 is a real number, and that x1 all the way up to, all the way through, every single real number is in there. Well, then what we're going to do, we're going to make our lives a little easier. We're going to move to a subsequence. So then there is a subsequence which we'll call xn, right? I'm not going to write xnk because we didn't define the original sequence. So it's just one more thing that we would have to write. So just call the subsequence xn. And this contains all real numbers in the interval 0 to 1. Okay, so all I'm doing is I'm saying, okay, you can write every real number in a sequence, then comb through that sequence and just give me the ones that are between 0 and 1. Okay, that's my subsequence. And I'm going to call that thing xn. Now, again, subsequences are themselves sequences. And so then let's denote the xn as follows. So I'm going to write them out. I don't know what they are, but I can write them as x1 is equal to 0.1, 0.2, 0.3. Actually, we need double subscripts here. D11, so that's decimal from x1 in the first position. D12, decimal from x1 in the second position. D13, third position. D14, all the way up. D1k, and these are infinite decimal expansions. Then bear with me, I'm going to do the same thing for x2. So you have D21, decimal from the second element of the sequence in the first position. D22, D23, D24, all the way up to D2k, and so on and so forth. These are infinite expansions, even if it's a bunch of zeros on the end, right? 0.1 is the same as 0.1000000. That's perfectly fine. 0.D31, D32, D33, D34, and so on, 3k. And what you can see is that this is sort of starting to look like a little matrix again. So dn1, dn2, dn3, dn4, dnk, and so on. Okay, so I've listed every single element of my subsequence, of my subsequence of all of the real numbers between 0 and 1 listed as a sequence. So all I did is I said, okay, they exist, put them in this sequence. Let me write them out. I don't care what the D's actually are. They're just numbers. They're numbers between 0 and 9. Okay, we will obtain a contradiction by constructing. So we're gonna build a number x between 0 and 1 that is not in the sequence xn. Now, why is that going to give us a contradiction? Well, I said that every single number between 0 and 1 is in that sequence somewhere. But I'm going to show that we had to have left something out. There's no way that we could do this. So here's what we'll do. Right? So let's say x is equal to 0 point, and let's make our lives easy. We're going to call this C1, C2, C3, C4, C5. Right, so I wrote down its decimal expansion, and then we will define, so that C1 is equal to, this is going to give us, so we'll have some cases here. So if D11 does not equal to 0, we will let this thing be 0. And if D11 is equal to 1, or sorry, if D11 is equal to 0, this thing will be 1. Okay, so just bear with me for a second. I'll explain where all of this comes from. This is going to be 0 if D22 is not equal to 0, and 1 if D22 is equal to 0. And in general, C sub k is going to be 0 if DKK does not equal to 0, and 1 if DKK is equal to 0. Okay, so what is it that I've done? Let's take a look at our decimal expansions above. I have used this number, this number, this number, so on and so forth. I took every single diagonal element. So from the first element of sequence x1, I took the first decimal point. From the second element of the sequence, I took the second decimal point. Now, here's the exciting piece of this, right? The exciting piece is that my element of my sequence cannot, or my element x cannot be in that sequence. Why is that the case? Well, its first decimal point, C1, is different from x1. So since C1 does not equal to D11, this implies that x does not equal to x1. Right? It has a different first expansion, 0.1 something, and then 0.2, 0.0 something. Different numbers, right? They have different decimal expansions. And C2 does not equal to D22 implies that x can't equal to x2 because it has a different second digit. And in general, x does not equal to xk since ck does not equal to the kth element in the decimal expansion of xk. But then x is not in the sequence xn. And so we have a contradiction. Therefore, R is uncountable. Right? So what this shows you is that if you try and list every element of the real numbers, I can always find something that's not in that list. So if you came to me and you said, no, Jason, I did it. I swear I did it this time. No, you didn't. There's no way that you did, right? And the reason for that is I can always just construct numbers that you didn't find in there. And the way you do it is you say, okay, what's your first number? Okay, I'll find a different first digit. What's your second number? I'll find a different second digit. What's your third number? I'll find a different third digit. And that way you can tune and you can build these numbers that couldn't have been included in the list. The other thing that I want you to see is think about like how simple it was for me to define this. I could have defined infinitely many other numbers that weren't in that list, right? So not only is there not one number in that list, but I could have said, let C1 be 0 or 2, or 1 or 2, or 2 or 3, or 3 or 4, right? And I could have done this for every single digit. I could have picked different things. So, you know, it's not just I didn't find one number in there. There's a ton that we're missing. And that's what uncountable really means. It means it's a way, way bigger set. There's so much in there that you couldn't even come close to counting that thing. And that's really the sort of magic of what we've talked about in this lecture, that the rational numbers, which you probably think of as being huge, you should think of them as being huge because they're dense. They can be used to approximate any real number. But in this case, we kind of got contradictory information, right? The contradictory information was that, well, apparently they're actually pretty small because they're countable. Now put yourself in the shoes of Georg Cantor in the 1800s and his, his many contemporaries in mathematics at the time, and trying to convince people that, in fact, the rational numbers are countable, but the real numbers are not. This is mind-blowing, right? This is mind-blowing for me the first time I learned it. Hopefully it's mind-blowing for you, but think about, these sort of mathematicians who didn't have all of the techniques and the tools and even just, the sort of thought process to get them up to this. And think about how controversial these statements probably were when they were first introduced.